seems you've caught me filling up my knapsack with a few items from my kid's toy box. Turns out I have an empty knapsack here and I'm trying to sell some of my kids' toys. But you see, I only have a certain amount of capacity in this knapsack, and each toy can get me a certain profit when I sell them. But each toy has various sizes, and I can only fit a certain amount into the sack. So I've got a difficult question at hand, which is, which toys am I going to put in the knapsack? So we're going to talk about how the 0-1 knapsack problem is formulated. So before you on the screen, we see the formulation for the knapsack problem, where B sub I represents the profit of item I, and X sub I represents whether the item is placed in the knapsack. Our conditions for the knapsack problem is, of course, the capacity. So W represents the overall capacity of the knapsack, and W sub I is the weight of each item to be placed in the knapsack. And we see that X sub I takes 0 or 1, so it's a binary variable. And we have N items for the knapsack. So I think the best way to move forward is, as we think about this, let's think about it in terms of an example. So if we have a knapsack with capacity 5, and the weight of each item is 1, 2, 3, respectively, and the profits for each item is 5, 3, 1, what we'll see is how we can use dynamic programming to solve this problem, but also how we can reduce this problem into a shortest path problem, for which we will apply a ranking procedure by Kata Murty and Eugene Lawler that was presented back in the 1960s and 1970s. So before we jump into talking about how we can rank the solutions to the 0-1 knapsack problem, we're going to first talk about how we find the optimal solution, which is done via dynamic programming. So the expression on the screen right now is the equation that we will use to calculate each value of a table that we will produce, that then we will be able to backtrack through to get the optimal solution. So the crux of this expression lies in solving for the maximum of looking at the previous row and whether we want to add in the next item or not add it in, depending on the weight. And we'll see this through our example, but this is the expression that we're going to use to fill in the dynamic programming table. So to set up this table, and again, we're going to consider our example that we previously introduced, we're going to put each possible weight capacity of the knapsack as a column. So with a capacity of 5, we have columns 0 for 0 weight, 1 for a weight of 1, and so on and so forth. And then for the rows, we're going to have each item. So again, if there's no items in the knapsack, that's 0, and then item 1, 2, and 3. So we're going to start by adding in the first row, which is to say item 0 with a weight capacity of 0. Well, of course, that's just going to result in 0 profits. Now, when this starts to get a little bit more exciting, is when we start looking at the first item. So if we try to add item 1 to a weight capacity of 0, well, of course, there's no profit. We can't put the item in there. But when we put item 1, which has a weight of 1, into the knapsack where we have a weight availability of 1, well, of course we could put that in, and that's going to give us 5. And the same goes for 2, 3, 4, and 5. So then we look at item 2. Again, if there's no room for item 2, well, we just don't have any profits. But we look at a weight capacity in the knapsack of 1, and we consider adding item 2. Well, item 2 weighs 2 pounds, so or has a weight of 2, so we can't really add the item into the knapsack. So, of course, the best possible scenario there is to keep item 1 in there, which has a profit of 5. Same goes for 2, right? Again, because we have a weight capacity of 2, well, we can't really put the scenario is we can keep item 1 in, which has a weight of 1, and a profit of 5, or we could put item 2 in, which has a profit of 3, but we can't put both of them in, right? We can't put items 1 and 2 in because, well, then that would surpass the weight capacity of 2. And so the best possible scenario here is to just keep item 1 in there, which has 5. But once we start reaching a weight capacity of 3, well, then that means I could put item 2 in there, in which case I could have item 1 and 2 in the knapsack to give me a profit of 8. And my only other alternative is to keep item 1 in there, which has a profit of 5, or to put item 2 in, which only has a profit of 3. So the best possible scenario there is to keep both the items in there. And we continue to fill out the chart in a very similar fashion to then complete the table of values for which we can then find the optimal solution. So we look in the bottom right corner here and we see that the optimal solution is 8. And then we can backtrack through this table to find which items need to be in the knapsack to give us that result. And so if we take item 3 out, well, we see that item 3 never gave us any benefit, so therefore item 3 was not in the knapsack. So then, if we take item 2 out, well, that had a weight of 2, so that puts us back down here to 5. So we see that item 2 was in the knapsack. And so then, once we remove item 1, we're back to 0. So we see that items 1 and 2 comprise the optimal solution, which gave us a solution of 8. We're now going to talk about Murdy and Lawler's general algorithm for computing the k-best solutions. Now, Murdy originally developed this algorithm as it related to the assignment problem. Lawler took it a step further and made some minor changes to it in order to solve for the k-best solutions to the shortest path problem. But the general structure and concept between both of them really remains fairly similar, and that's what we're going to cover here. So in the first step, they compute an optimal solution and place it in a list, setting k equal to 0. Now, the solution that is similar to both problems is a solution vector of 0, 1 variables. In the next step, they remove from the list the least costly solution. In both of Murdy and Lawler's cases, they are minimizing their respective problems. And they pull out the kth solution in order to create a series of subproblems. Of course, if the kth solution is equal to k, then it stops. And that's what step 2 is all about. But step 3 is really where the bulk of the work is done in creating subproblems by changing each variable of the kth solution sequentially. So they do this iterative set of subproblems, really forcing a minor change in each subproblem while fixing certain variables. And this is where the key difference between what Murdy does in the assignment problem and what Lawler does in the shortest path problem is that in their respective problems, they're leveraging the framework of the problem in order to create these subproblems. And this is what we're going to do in our dynamic programming example. But first, what we want to do is really just establish this general procedure and algorithm. So in this series of subproblems, they're going to recompute for each subproblem the optimal solution given certain solution variables are fixed. And that's what step 4 is done, is computing those optimal solutions and then adding those solutions to the list and then returning to step 1. And that is the essence of the general framework that Murdy and Lawler utilize to generate the k-best solutions for their respective problems. We're now going to create the graph from the 0-1 knapsack problem. And we're going to do this so that way we can set up a shortest path problem for which we can apply Eugene Lawler's k-best rankings to the shortest path problem. So to do this, if we think about our example that we have, where we have 3 items that we're looking to place into the knapsack of capacity 5, we're going to first look at the first item, and we're going to imagine that we have the knapsack in one hand that's empty and the first item in our other hand. This is going to represent the first vertex, where nothing has been placed into the knapsack, and we're considering whether to add item 1 into the knapsack. So the next row of vertices represents item 2 and corresponding knapsack weights starting at 0 going up to the capacity of 5. So we're going to draw an edge from V10 to V20 if we decide that we're not going to place the first item into the knapsack. And we're going to give the edge the corresponding weight of 0, which represents the benefit of not putting the item into the knapsack. Now, as we think about our example, we also remember that the first item had a weight of 1. So if we put the item into the knapsack, then the knapsack is going to have a weight of 1 and a benefit of 5. We give it the edge a weight of -5 because we're establishing a shortest path problem. Now that we've taken care of the first item, we move on to the second item, where we essentially have the same scenario. So the third row of vertices represents item 3, but first we have to either get item 2 into the knapsack or decide not to put it into the knapsack. So we look at vertex 2, 0, and if we put the item into the knapsack, then that item has a weight of 2, and so we draw an edge from V20 to V32 and give it an edge weight of -3, which is the benefit of putting the item into the knapsack. Similarly, we draw an edge from V20 to V30 and give it a weight of 0 if we don't put the item into the knapsack. And we do the same thing for V21. Now we don't have to draw edges from the other vertices because there was never a decision to put the item into the knapsack or not into the knapsack. So then we create the rest of the graph in the following manner, or in the same manner, so that we then construct the graph of G. Now notice that the final row of vertices we label V star 0, V star 1, V star 2, and so on and so forth. This really just represents the final decision that we make with regard to the last item in the knapsack. So there's no item that we're going to consider in that final row. So we're going to draw from, in this case, from V30 to V star 3 if we add the third item into the knapsack, because that item has a weight of 3. So we go from having a weight of 0 to a weight of 3, and it's got a benefit of -1 in this case. And then our sync node is V star star, and that's really just to complete the network. So that way we have a directed acyclic graph for which we can find the shortest path from V10 to V star star using Eugene Lawler's algorithm. Now, the time complexity that Lawler cites for ranking k shortest paths is given as kn cubed, where we're ranking k solutions with n edges. So we think we can do a little better than that using the dynamic programming approach that is really quite typical to the 0-1 knapsack problem. So to begin with, we need to start by looking at really our step 3 subproblems. So recall back to the general algorithm procedure for ranking k solutions described by Murdy and Lawler. Step 3 of that general framework has a series of subproblems where we iteratively and sequentially change each of the solution variables after we've obtained an optimal solution. So what you see before you here are the n subproblems that we have to create. Now, the big difference in what Lawler does is we start at the very end of our solution vector. And we do this because we're going to take advantage of the dynamic programming table that we produce after we've obtained an optimal solution. So, for example, if the last solution variable in the optimal solution is 1, we're going to change it to 0 and leave all the other solution variables free in the first subproblem. In the second subproblem, we're going to fix the last solution variable as it is in the optimal solution, and then we're going to change the second to last solution variable so that it is, we're going to force it to be different than what it was in the optimal solution. So these iterative problems or subproblems really force us to be able to find the next best solution. And when you think about it, it makes sense, right? If we have a solution vector of zeros and ones, and we say, okay, we're gonna change the last variable, well, that means that if the next best solution it exists in such a way that the last variable is not part of it, then we're going to obtain it. And by sequentially going through these subproblems, we're guaranteed to find the next best solution. So the next question that naturally arises is, how do we take advantage of the of the pre-computed values in the dynamic programming table? Now we're going to do that by the following expression, where these summations, given the framework of dynamic programming, we don't have to go through and iteratively sum all these values, and we'll see that through our example. Rather, we can just go ahead and recompute these every iteration that we solve these subproblems. But what we're doing here is we're reaching back into the table to retrieve a solution when we restrict the weight and we restrict whether an item must be in the knapsack or not. And that's what this expression is doing. And we're going to see how this plays out here in an example. But first, let's take a look at the actual algorithm that we're implementing here. So what we're doing is this is the pseudocode that represents Lawler-Murdy's framework, but in the context of this dynamic programming problem, particularly the 0-1 knapsack. So we create the list of solutions, and then we're going to fill that list. And so what we see here is that while k is less than big K being an input for the number of best solutions we want to achieve, we're going to create the series of subproblems in the for loop, one at a time, and then we're going to reach back into D being the dynamic programming table, to really to retrieve the values that we need to retrieve in order to then either add them to what the profit is of the variables that have to be included given the weight restrictions. And then we just add those to another solution vector that then we will ultimately retrieve the next best solution out of. And those if statements in there really are just updating those summations that we saw in the previous equation. So that's our algorithm. Let's see how it plays out in the context of our example. So as you recall, we created this table that we'll call D, that gives us the optimal solution. And we found the optimal solution where the first item and the second item are included. And so what our algorithm does is it creates the subproblems. And so what you see there is the subproblem where x3, or representing item 3, must be in the solution. And then the next subproblem is where x3 is not in the solution, but x2 is not in the solution either. And you can see that that's negated from the optimal solution. Let me go ahead and pull up a laser pointer here to better reflect what I'm talking about. But you see that x3 here is negated from what it was in the optimal, but then in the sequential subproblems, that's left into the solution. We're forcing it to be 0. Similarly, for the second subproblem, item 2 is not in there, even though it was in there in the optimal, but then in the third, we put item 2 back in there. Okay, so that's the subproblems we create. So we want to solve for each of these subproblems given this table. And of course, here's our information that we're going to pull from. So right away, we should notice that the dynamic programming table itself doesn't give us the next best solution. And with such a small example, we can see that the next best solution, given our example here, would be having items 1 and 3 in the solution, which gives us a value of 6. But there's no 6 to be found in the table. So applying these subproblems is how we're going to be able to find it. So to solve the first subproblem, what we do is we know that x3 has to be in the solution. So that corresponds to a weight of 3, which means we restrict our table given by subtracting off a weight of 3. So now our weight capacity is only up to 2. And we see that optimal solution comes from having a 5 here. And where did this 5 come from? Well, that really just comes from having item 1 in the knapsack. So the optimal solution when item 3 has to be in the knapsack is given by 1, 0, 1, and that gives us an optimal solution where of 6. Okay. So the next thing we're going to do is we're going to solve the next subproblem where we negate having item 3 in there, right? And then we negate having item 2, and that means really the capacity of the knapsack is all available. And so when we solve for that, now we're just looking at this part of the table because it's just one item that can be in the knapsack in this example. And we find that gives us the optimal solution of 5, and that is given by 1, 0, 0. And then finally, we look at the last subproblem, which really just fixes all of the rest of the variables. And that gives us a solution of 3. Okay, so what we did is we solved for all the subproblems, give us at least one of those as the next best solution. So using the dynamic programming table really gives us a much better time complexity than had we reduced it to a shortest path problem to apply Lawler's specific algorithm for that. So in Lawler's paper, he cites a time complexity of OKE cubed, where E represents the edges. To our problem, that translates into 2n w plus 1 edges. And so, of course, that gives us an O of k n w cubed. However, in our dynamic programming example and looking at the algorithm, we achieve a much better time complexity of n k plus w. And that's given, can be seen in the algorithm that we previously described, where taking into account that the dynamic programming time complexity for the 0-1 knapsack is nw, and then ranking k of those solutions is nk, and so we get nk plus w as an overall time complexity, which is certainly much better than what we could do in the shortest path reduction. Well, hello again. Boy, that was some exciting stuff. You know, we not only covered what the 0-1 knapsack problem is, but we talked about how we can rank the k best solutions to the 0-1 knapsack problem. We also talked about how we can reduce the 0-1 knapsack problem into a shortest path problem. And using Murdy and Lawler's framework for ranking k best solutions, we showed that we can leverage dynamic programming to beat Lawler's algorithm when it comes to the 0-1 knapsack problem. I don't know about you, but I'd say the future's looking pretty bright.